Hello! Today we're going to be starting Chapter 5, Protein Function. We need to keep in mind that when we're talking proteins, we're going to see that proteins, for a large portion of our cellular metabolism, it's going to be based on proteins acting as enzymes. Okay? Acting as enzymes. What they're doing is they're being a chemical catalyst. A catalyst, if you remember from your chemistry, is nothing more than a metal or substance that sparks a reaction. Well, here, enzymes, as we're going to see in this chapter, spark a reaction. They take something that would occur on its own. That reaction could take minutes, hours, days, weeks, months, years to occur, but they make it happen on a much smaller scale. Minutes, seconds, milliseconds. And they do it in such a way that it requires less energy to kick off the reaction. Now, when we look at proteins, enzymes, this chapter, there's a few principles we need to take into account. First is that proteins, these enzymes, function by reversibly binding to their substrate. Binding to their substrate. We refer to the substrate here as the ligand. Anytime you have a protein that interacts with something else, that something else is a ligand. For enzymes, taking an substrate, turning it into a product, that ligand happens to be the substrate. For other protein interactions, what we'll be talking about, it could be other proteins, it could be other organic compounds. Key term also there that I just stated, and it says right here, reversible. Okay? This is not a one and done, it's bound and never going to be unbound. It interacts with via R groups just long enough for something to occur. This interaction is going to occur in what is known as a binding site or active site. The ligand is going to have a specific size, shape, charge, whatever it takes to get into that active site. And once in there, has the correct size, shape, charge, whatever, to interact with the R groups of the amino acids of that polypeptide making up that enzyme. Our third principle is that proteins are flexible. They are not set in stone. That shape is not set in stone. That shape, there will be a conformational change, a change in shape once that ligand, that substrate, enters into the active site. The rest of the protein will fold around it. We're not talking big changes in tertiary structure and quaternary structure, just slight bends, slight twists, whatever it takes to get all those R groups of the amino acids of the polypeptide making up the enzyme to interact with the ligand, the substrate. They refer to this conformational change as the induced fit. Only the true substrate, only the true ligand for that enzyme will result in an induced fit. We see that in the natural world, that there are quite a few other organic compounds, organic structures, that have a close shape to the true ligand, to the true substrate. They can fit into the socket. They can fit in there to that active site of the enzyme. But since they don't have the correct shape, the correct charge and all of that, not all the R groups will be able to interact. Thus, there will be no induced fit. There will be no conformational change. As a side note, this is the basis for many of our enzyme inhibitors that we find in nature. Things that have somewhat the right shape, can fit in, but aren't the true substrate. Thus, there will be no product form. Once they're in the active site, the enzyme can't interact with its true ligand, thus no product can be made. The product level, the concentration of the final product, decreases because of the presence of these competitors. And then finally, some of the proteins, some of the enzymes that we see in the cells are not a single polypeptide, they're multi-subunits, and that the conformational change of one affects the other subunits in a positive or negative fashion. And as in everything we see, everything we know, everything's got to be regulated. You cannot have things occurring willy-nilly. There has to be some level of control.